Welcome. This is the next chapter in physics, and this chapter is all about waves. Now, we have done about optics. We've finished that. If I haven't, then you might want to check out my other videos. So we're gonna go over waves quite quickly, hopefully. Within 15 minutes we'll go over the whole topic of waves and what's so good about them. Okay, so if we go from the start actually. So very basic, transverse waves are waves which oscillate at right angles to the direction of motion, and longitudinal waves are waves which oscillate parallel to the direction of motion. So they're the two waves. Types of transverse waves is all electromagnetic waves, which can easily cover, you can think of two waves of that, and longitudinal waves could be waves on a slinky, or sound waves, or waves on a water in the sea. Now, there's a couple of things you need to know about transverse waves. Transverse waves can be polarised because they are not plane polarised before, say. So this is an unpolarised wave. I'm going to draw a diagram for it. So that is an unpolarised wave. So it operates on two planes, the horizontal and the vertical plane. I don't know if you can see that. Yep, so that oscillates on the horizontal and the vertical plane. Now, you can make this go through one plane. Say this is the wave before, and it goes like that as well. So it's at right angles, and if you can see that, it's at right angles as well. Now if we put it through a filter, that's vertical. Well, it's not actually vertical, that's just the way the molecules are aligned to allow it to go like this. Then you will get only the waves that can do that are fit through there. You've got to make sure the aperture, so the width of it, is the same width as the wave, which still is quite hard to do, but if you make it like that, you get a plain polarised wave, which looks something like that. And the uses for this are polarised sunglasses, which protect your eyes and absorb some of the sun's energy in terms of light. That's pretty much it for the start of waves. We're going to go on to the measuring of the waves. See how long we've got. Yeah. So hopefully you got that. Oh God. If you didn't, just drop some comments in and I'll try to get them answered. Oh dear. So you got a couple of things you need to know. I'm not going to write them down, I'll just talk to you. So the displacement of anything is the distance and direction. And of a wave, of a particle in a wave, is distance and direction relative to its equilibrium position, which is the line that you see. So that, say it's a wave, equilibrium is there, and that's called a node, which we'll go into in a minute. So the amplitude is the maximum displacement of a particle, which is that bit there, A. That's the amplitude of a wave, because it's the highest point on a wave. The wavelength is the least distance between two adjacent nodes, so two peaks or two troughs, for example. That is the wavelength. It's also represented by lambda. The one complete cycle of a wave, which is basically the wavelength. The frequency is the number of cycles that pass within 1 second. It's measured in hertz. The speed of a wave, I did mention this before, equals CF lambda, and the speed of a wave in air is 3 times 10 to the 8, which is very fast. And if you want to measure speeds in different substances, you can look at my total internal reflection and optics videos for that. Now the phase difference. Now this is, a wave is not just a line, it's made up of individual particles. So let's draw the wave. And this was, light for example acts as a wave and acts as a particle. So let's draw a wave. Now this, what I'm going to draw here, just to give you a bit of an insight to what we're going to do in a few minutes, it's called a first overtone. And I'll explain a bit more about that in a few seconds. Now, if you can imagine, these are massive particles. Well, actually very small, but they appear massive on there, but trust me, I'm just rubbish at drawing. And the phase difference is the difference between the two vibrating particles. Ooh, don't worry, my hands are up here, not below the camera. So, they're up here. Ooh. And the phase difference is the difference between the two vibrating particles that you're talking about. So, the phase difference is 2 pi d over, show me that's right, over lambda, yeah. Now, obviously you know what pi is, the 3.1, it's a standard given figure. The lambda is the difference in, yeah, so d is the distance of the wavelength, so it could be half a wavelength or half a metre or etc. And y is the wavelength. Now distance is, so you've got a wavelength is 2 metres, and at the node you've got a particle which is halfway long obviously, so it's a fundamental that's behind me. Then the distance would be 1 metre and the wavelength would be 2 metres, so it would be 2 pi 1 over 2, so it would be just pi 2.1. Just to give you an example, and the way I look at it is pi is equal to 180 degrees, 2 pi is equal to 360, and half pi is equal to 90, and 3/4, yeah, you go up in as such. So yeah, so half pi is 90, pi is 180, 2/3, you know what I mean, 3/4, sorry, is 270 degrees, and 2 pi is, so each time you add half a pi on, sorry, that's right, it's 90 degrees. That's just the way I look at it, but so but a radon is 57.3 degrees, but the way I look at it is through looking at the pi. I mean, you can look at other videos on YouTube which will give you a bit more in depth explanation to this, but the way I look at it is just in terms of pi, really. That's just the way I do it. So hopefully you've got that. Again, if you get any questions, just give us a comment. Try to keep it nice. Don't be an idiot. Right. So we're gonna go into wave properties now. So long got left? Yeah, we've got a bit. Okay, so I'm gonna start going a bit slower now. Hopefully you got that pi thing. Yeah, so you may have done this at GCSE. What I'm going to draw now is a wave tank. So this should be horizontal. And you've got a rippler, and there'll be a flashing light somewhere. So that'll be on, off. And then, this is full of water, so it does this. Because that is the thing that's vibrating. In the centre of the, that was quite creepy eyed, but if you're still here, well done. If you've died, sorry about that, but you did risk it watching the video, so I'm blaming your phone. Yeah, so the waves observed in a ripple tanks are called wavefronts. So these things are wavefronts. However, the crest is perpendicular to the wavefront. So if the wavefront's going this way, the crest is that way, that's perpendicular is 90 degrees, and you can see that is 90 degrees. So wavefront, that is a very simple analogy. Wavefront and wave crest. Now when I say it's at right angles, what I mean is it travels at right angles. So the wavefront travels right angles 90 degrees to the wavefront. So if the wavefront's going that way, it's going that way, the wave crest. Hopefully you've got that. If you haven't, obviously again just send us a message. Now, the reason I've rushed a little bit is to get onto the final bit, really. Of stationary and progressive waves and the fundamental overtones, etc. So, a stationary wave, I'm just going to explain it now because I don't need to draw it up. So, a stationary wave is where it's sort of it's when two progressive waves meet and it causes a stationary wave, which is, as the name suggests, stationary. So, you've got two progressive waves, and two progressive waves are waves that are going up and down, you know, big waves. Transfer energy is the definition in the textbook. Say, this is how a standing wave is formed, just give you a quick overview. So a standing wave could be going like this, no, progressive wave, yeah, one going that way, and then the dotted line represents another going another way. And that is two waves, and then they create nodes and antinodes. Antinodes is the difference between the two amplitudes, and a node is a zero displacement where it's along the line of the wave. Now hopefully you've got that. So the two progressive waves combine nodes and antinodes to form a stationary wave. I mean, you could go a bit more in detail than that, but that's the basics for it. I'm assuming that you've already gone over the stationary waves. Now we're going to take a break there. Sorry. Well, yeah. We're going to take a break there. And now in the next video I'm going to go over the stationary wave, the overtones, and see you in the next video.